let's talk about the magnetic force on a current carrying wire. Now we've already seen the magnetic force on a charge. If a wire carries current to the right, that means that positive charges are moving to the right. This is conventional current. Thus, we can still use the magnetic force on a moving charge right-hand rule to find the direction. So this wire is an external, an external magnetic field that's pointing out of the page. So out of this page here is a magnetic field that's caused by something else. Could be a magnet, could be the Earth's magnetic field, and it carries current to the right. The question here is, which way is the force on this current carrying wire? Let's first show the B field direction. The external B field is pointing this way. That's the symbol for pointing out toward us. And then we're going to draw one moving charge of the current and show the force vector on that charge. If we have a positive charge, if the current's to the right, which way is that charge moving? It's also moving to the right. So the velocity of the charge is to the right. Now we're going to show the direction of the force. Well, we got to use our right-hand rule. So we've got the velocity this way. We've got the magnetic field coming out of the page, which for you guys looks like that. So which way is the force? The force is the way your thumb points, as long as your thumb is perpendicular with your hand. V cross B, force is down. So the force vector on this particle as it enters the magnetic field will be down. That's the direction of force. All the forces on the individual moving charges add up to the net magnetic force on the wire. Let's introduce this equation, then we'll derive it. So the magnetic force on a current carrying wire equation is this. The magnetic force, F sub M, or sometimes F sub B, depending on your textbook. This is what the AP uses. This is a vector. It will be equal to the current times the length of the wire segment, and this is a vector. It's in the direction of the current. Current's not a vector. You can make a vector L, which is in the direction of current, conventional current, and then you cross that on the magnetic field so that the magnitude of that magnetic force is equal to ILB times the sine of the angle between L and B vector. Let's go ahead and derive that right now. The magnetic force, as we saw before, is Q times V cross B, but the velocity of the charges that matter here is the drift velocity. So Q times V drift crossed on B will give you the force on an individual electron. How do you figure out the force on the wire? We got to figure out how many electrons are
mobile in that part of the wire.
Well, that's not difficult at all. This little n, you may recall from last time, that is what we call the charge carrier density. It's the number of charge carriers per unit volume. How do I get the volume of a wire? The cross-sectional area of the wire, if here's my wire, this right here is the cross-sectional area, times its length. So this is the volume of the wire. So notice that this will be the force on one electron times what is this whole thing right there. That is just the what? N times A times L is the number of electrons that are moving in that section of wire. So it's the force on one electron that's moving with drift velocity V times all those electrons that are moving in that section of wire. Don't forget, well, I never. And when you have electrons as your charge carrier, that's what this is. It's just E is the elementary charge of our charge carrier there. So by just plugging that in, the force on a section of wire is the current through the wire times the length of the wire, and this L is a vector right there. That L vector is the length of wire in the direction of the current. So the L vector is got a magnitude of the length of the wire, and it points in the direction of current. Notice that current's a scalar, but L is a vector. You do IL crossed on the magnetic field for a straight wire. Now, for a curvy wire, there's a fantastic way to do it. You could integrate. You could do this. You could integrate every little piece ds of that wire and add up, multiply that by, so you could do the infinitesimal force on a little infinitesimal piece of wire. df is I times that. I've labeled a ds over here, and unfortunately I labeled a dl over here. It's that infinitesimal length cross b, and then you integrate that, adding up all those. But there's a really easy trick. If you just call this vector right there that starts at the beginning of the wire and ends at the end of the wire, when I say beginning and end, it starts where the current starts and ends where the current ends. That L prime, the whole force on this thing is just IL prime cross B. So you don't have to do any integration. If you're trying to find the force on a curly wire, all you do is you draw a line, which is, we're going to label that vector L prime, from the start of the current to the end of the current, straight line, and just cross IL prime crossed on B, and you've got the force on that whole curly wire.